Okay. Let us start. We'll see later on. So we were doing shock waves last time. Okay. So shock waves are the events where traffic flow is disturbed, and then normally when the capacity is decreased, and there can be different types of shock waves. Okay, we looked at different types, and then we derive the equation for calculating the velocity of the shock wave, which is basically how the Q will extend. Okay, when the shock wave happens, how the Q will extend or clear. So these are the two flow values before the shock wave, after the shock wave, and the two densities before and after. Okay. So if you know the speed multiplied by time will give you, right? The speed is just one time, right? Multiply speed by time, you get distance, length. So if you are calculating it for, is the signal? Yes. So now this is the case for a signal. Okay. So a signal, we have frontal stationary shock wave. The signal becomes green, the front becomes stationary, right? Nobody moves. So we have frontal stationary shock wave. Okay. So we were using in this equation, if you see here, we are using Q1 and Q2. Okay. Q1 is flow before shock wave. Q2 is before, after shock wave. Signal becomes red, flow becomes 0. So this becomes 0. Okay. When cars are stopped at a signal, they are stopped at minimum spacing, right? They try to get as close as possible. Okay. So when the spacing is minimum, density is maximum. Okay. So we call that as jam density. So there was Q2 here, I replaced it with 0. So gone. And there was K2 here, I replaced it with Kj, jam density. Clear? I wanted to multiply by T, right? Time. How much is the time? The time when the signal is red. So R. Okay. So velocity into time gives you length. Got it? Okay. Now, if you look at this diagram, okay, so on this axis I have time, on this axis I have, on this axis I have distance, okay, time, distance, okay. So, yeah, see, this is the time when the signal is red, okay. So there is a shock wave, which is because of the signal. Signal became stationary, you started the shock wave. So this is the shock wave. Okay, this is the Q. And when the signal becomes green, the people will start moving, right? But the entire Q will not go immediately. It will take some time, right? The signal becomes green, the Q takes some time to clear. Okay, this is this time. The time taken by the signal to become green. The time taken by the signal to clear the Q. Okay, so this is when it is actually red, the Q is building. This is when the Q is clearing. Okay, when the Q starts to clear, now you have people who are coming from behind, they are joining the Q. And the people who are at the front of the Q and they are moving, right? Now we have two shock waves. One which are clearing and the one which are joining. So that's why you see two lines. Okay, these are the people who are joining. These are people who are going from the front. And when these two meet, no Q. Got it? Okay. So this angle is basically the velocity of the shock wave. The angles which you see are the velocity of the shock wave. Okay. So this one is backward forming and this one is backward recovery. So this one is the forming one, this one is the recovery one. Recovery means they are moving from the front, right? These are those people. Okay. So now we come here. Okay. So the recovery shock wave, we are representing it with omega 3/4. Omega 3/4 is a recovery wave. Okay. So the speed will be the slope of distance and time, right? Okay, so if I know the angle, slope is tangent. Clear? If you know the angle, the slope is tangent of the angle, right? This much is clear, right? Okay, so the speed of the shock wave is distance upon time, which is tangent of this angle. Clear? Okay. Now, if you look at this triangle, this is my base, this is my perpendicular, right, for this angle. Okay. So tangent theta is perpendicular upon base, right? Perpendicular upon base. Okay. Perpendicular base, tangent theta. Okay. So, and for this triangle, okay, again, this is my angle, this is my base, this is my perpendicular, right? The perpendicular is still ST, but the base is the whole thing, right? Okay. So this is what you see, but the other tangent. Okay. Now, if tangent gamma equals to ST upon RS, then RS equals to ST upon tangent gamma, right? We just switched it. Okay, clear or not? Okay. So RS equals to this thing. Now in this equation I have RS. So I will replace RS with this one. Okay, clear? Now, what am I trying to calculate? Length of the cube. This thing. ST. Okay, so in this equation or this equation, I had two unknowns, RS and ST. Yes. Okay, so what we are doing is we are replacing RS with this one. Got it or not? Okay, I have two triangles. Going back, I have two triangles, this one and this one. Okay, the value I am trying to find out is ST. Okay, these are two shock waves, so their speed is tangent of this, the slope. Okay, so I took this triangle, the slope is this, and I rearranged the equation for RS. Okay, and then I took the other triangle and I rearranged it for ST. Now the ST equation has RS, which I can replace from here. Okay, clear or not? Okay, so in the end I get the equation for ST, which is this one. Okay, so this is the equation after replacing RS. Okay, so this was the equation. I took ST on one side, everything else on the other side. In this equation I had RS, which I replaced from here. Okay, now in this equation you can see we have tangent phi and tangent gamma. What is tangent phi and tangent gamma? The velocity of the two shock waves, the forming shock wave and the recovery shock wave. So tangent phi and tangent gamma are replaced by the recovery values, the speed values. Clear? Okay. So now I have length of the cube in terms of R signal timing, length of red signal, and the two shock waves. Yeah? Okay. Now, so I calculated ST, which is the length of the cube. Now to clear this length of the cube, how much time I need? This much. RS. Okay. So what we will do now, if you look at, where was it? This thing. Going back to the equation of this triangle. This one. Okay. So I used it for ST, right? Now I will use it for RS. Okay. So So from this equation, Rs equals to this. Okay, and I have St, and St equals to what? St equals to what? Magic, right? I already derived an equation for St. Right? Now I am trying to find out an equation for Rs. Okay? So I'll go back to the initial equation, rearrange it for Rs. In this equation I have St. This goes here. Okay? The final equation is this one. There is some cancelling out and opening the bracket and taking common and so on. Okay? I'm not going into that. Okay? Okay, now let us revise the terms. First thing is the easiest one. What is the small r? What is the small r you see in all the equations? Yeah, you can tell me what is small r? No, small r is not there. Okay, it's there, yes. So what is small r? The signal is right? And the time the signal is right, okay? And then we have 2 omegas, right? We have the 2 omegas. What are the 2 omegas? The shock waves, okay? There are 2 shock waves. One is forming, the other one is recovery. Forming when the signal is right. Recovery starts when the signal becomes weak, okay? And then we have what? We have Rs and St. Okay, so what is St? What is this? Length of the cube. What is Rs? Yes, it's a base in a triangle. But what is it? What is it? Okay. The cube will start forming when the R starts, but the cube will clear at time Rs. Time Rs. Got it? Clear? Okay, now we have some equations and problems. So we can use these equations together. Okay, we have seen the equation which we derived in the last lecture, which was this one, the basic one. The speed of the shockwave applies anywhere, no problem. Apply. Even the equation for the signal is coming from here, right? Okay. And then we have the other equations, which are obviously the length of the queue and the time to clear the queue. This is related to the signal. Okay, this is related to the signal. Okay. So we have a signalized intersection which is carrying 1000 meters per hour per lane. Velocity is 50 miles per hour. The duration of the red signal for this approach is 15 seconds. Okay. Saturation flow is 2000 meters per hour per lane. I'll come back to it why we need saturation flow rate. Okay, with a density of 75 miles per hour per lane, the jet density is also given, which is twice of the density at saturation flow. Okay, we have to find out the following: length of the queue at the end of the red phase. Length of the queue at the end of the red phase. Maximum length of the queue. The time it takes to clear the queue. Okay, clear or not? Okay. Now, for the first thing, okay, length of the queue at the end of red phase. Okay, at the end of red phase. Now, Q1 was the flow before the shock wave, right? Here the shock wave is because of what? What happened? What caused the shock wave? Signal, right? Okay, so what is the flow before it reached the signal? 1000. Okay, so we know Q1. Okay. is again density before the shock wave. Okay, before the signal became red. Did they give me density? Do I have the density? No? What is it, 75 and 1? These are densities, right? These are densities. Can I use them? Can I schema? Any of them? Yeah, two values. They are what? After the shock wave, yes. You were saying them? Cannot do it. Why? After not before? How do you know that? Okay, very good. Yes. So these densities are at this flow, okay, not at 1000, okay. So to calculate density at this flow, I'll use the basic equation of traffic flow, which is yes. So flow equals density into speed. Flow is given, speed is given, we'll calculate density. Yes. Ah, 20. Okay, so my K1 is 20 and Kj is jam density, which is given. Okay, so now I can apply this equation to calculate the length of the queue at the end of red phase. Okay, so this is the length of the queue here at this point. So you can see maximum length is here, not here. Okay, so R is 15 seconds, 1.5. This is 1000. This is 20. This is 150. How you got it? I'll call it L1. 15 into 1000 upon 20 minus 1. R was given, Q1 was given, we just calculated K1. Yes, how much? No, nothing. All of them are in the same units. Ah, yeah. Flow is in hours. Yeah. Sorry? Yeah, because L1 will be in feet. Okay, and your density is in vehicles per mile. Okay, so you can like convert it to feet now. Multiply by 5280. You convert it to seconds, right? Okay, divide by 3600, right? So 15 divided by 3600, and then something like this, right? So what you are getting is in miles, basically. Miles, yeah. Miles. Ah, no, sorry. Why miles? Because we have 20 minus 150, yes. Because we have 20 minus 150. This is in minus. Okay, so now you multiply with 5 to 80. Minus 60.
No,
1 only 5 to 80. Don't worry about minus. 1 6 6 7. Okay, you multiply with 5 to 80. 5 to 80. Yes, right? 169 point what? Okay, now why minus? Because it's a forming shockwave. Remember, length is speed into time. Shockwave speed is negative. Shockwave is creating a Q, right? Where? Forward or backward? The Q is extending where? Forward or backward? Back, right? So minus. Okay? And you multiply minus with time, it will remain minus, right? You don't have any cancellation. So that's why. But we should understand that this is basically just showing that it's method.
So we don't need to write minus.
We don't need. Okay? So this is the length of the Q at the end of the red phase. Okay? Now, for the other two questions, they are asking for ST and RS basically. ST and RS. Okay? In both the equations I am using R, I know R. Okay? But they are using these two, what do you call it? These two velocities as well. The shockwave velocities. One for forming, the other one for recovery. Okay? The one which we used here, which one is this? Forming, right? We did not clear the Q yet. Okay? So forming one is 1 3. Okay? But without this. Okay? So now remove this. This was for conversion, right? So remove this. And what else? We will keep it. So remove this as well. So remove the time and the conversion factor. How much you get? W13. How much? Minus 7%. Okay. Now, I need the other one, which is after the signal becomes green. Okay. Now, so I will go back to my initial equation. The first equation for this one, which is general equation for velocity of the shock wave. Okay. Even this one, the previous one also came from here. Okay. So I need. Now remember, we are talking about recovery shock wave. Okay, so this is after the signal became green. So before is red, after is green. Got it? Clear? When the signal was red, what was my flow? 0. Okay. What was my density? No. That was before, because 20 was at 1000 flow, right? Okay, so what is the density at 0 flow? No. Density becomes 0, there are no cars. Right? Does this mean signal becomes 0, no cars? No. Flow becomes 0 at what? Density. There is a name for it. 1 to 3 is what? Jam density, right? And jam density is completely jam, right? So flow is 0. Okay? So Q1 is 0. Q1 is 0 and K2 is jam. Okay? Clear or not? Signal opens. Okay? People are very close behind, they are waiting in the queue and now they are free. Okay? So they will try to do what? Go ahead go very slowly, right? Huh? They will take their time. Let me read some more messages. Who cares? Dr. Nash class. You can go later. Something like this? Yeah. Don't be so honest. Yes. You will try to do what? You will try to go as fast as possible, right? Okay. Yes. The cars will need some time to reach the speed. Okay, but eventually they will reach maximum flow. Because now, see, signal was red. Now it's green for you, and for others it is red, right? So only you are going. So the segment in front of you is free. Okay, so this will go at maximum flow. Okay, if you look at the question, they are calling it as saturation. Got it? Okay. So saturation flow is how much? 2000, and at this flow the density is 75. Okay. So this is what we take when signal becomes green. The highway actually does not reach maximum. It is just for that few seconds because the other flows are stopped and the segment is open now. It's completely free. That's all. Got it? And the cars were waiting. Remember, there's a queue. Okay. So going back to this equation. Okay. Now this is for recovery, right? Recovery we called it 3-4, right? 3-4. Call it 3-4. Okay. So using this equation, my Q1 is 0, my Q2 is the saturation. Okay. My K1 was jam, and my K2 is the one which I have at saturation. Just remember. Minus? Okay, these are not in miles per hour. Okay, both of them are in miles per hour. Speed, miles per hour. You keep it in miles per hour, no problem. Okay, clear? Now we can use these two equations and calculate ST and RS. Maximum length of the queue, time to clear the queue. Okay? Yes. How long will you use these values? Came to this class for some reason, right? You have the equation in front of you, you have the values, you need only three things, R and these two. R is 15 seconds. Go ahead. Come. I never asked anybody to sit there. You go there by yourselves. Although you cannot see.
R is
15 seconds. ST we have to find. W13 is this and this one is. Okay. Convert R to hours, okay, because values are in miles per hour. This one is also minus. This is also minus. Okay, both are minus.
What is the
Sorry. What?
0.03?
Yeah, in minus.
Is it
ST is in miles. Okay, because you put everything in miles.
0.02.
Miles. Where you still have to do hours. 0.02, right? Or something. So ST is 0.02 miles. Can you convert it to feet? Yes, hours. Yes.
Should I use that or
You can use this equation or this one. ST you already know. Tangent. This is R34. You can use this one as well. This one will be W34, and this one you know, and this one you already calculated.
So should I convert it to hours, right?
Or you should convert to hours because everything is in miles per hour. Then you will get the answer in hours. So it will be as some fraction.
Minus
What?
is it
3 hours.
minus 3.9.
Oh.
I used the double term.
Which
That's
one?
to 30 for the big 34. Term.
This one?
No, not
This one? Okay. So ST is
105.6.
no ST. Then you are putting this in miles per hour. So ST 0.02. So you have to be careful with the units with these equations. There are no conversions. You have to look into each factor. Okay. The speed is in miles per hour. ST could be in miles per hour or feet as per your.
Over 26.6.
Where you are taking ST in miles, right? So 26.6.
0.02 over 26.6.
3, 4. So then you just convert R into hours. That's it. And get the answer in hours. Multiply it with 3,600.
Why it's with the minus?
Because the speeds are minus. Will you put them in the minus?
Yes, minus 26.6.
Into minus.
7, minus 7. Okay. I think I'm guessing.
Yes. Now good. Okay, so I will just simply write it here.
0.0016.
Now
0.00.
this is an hours. Okay, so you multiply by 3600, it becomes what? 6.1 seconds. Okay, so this one was ST, which was 105.6. And what? 6.2 seconds. Okay, these last conversions are just to have the significant figures. Okay, but the conversion, the equations are important. Okay, otherwise you will be getting very bizarre results. Got it? Right? Okay, so for calculating the length at the end of the red phase, we use this, which is speed into time. Shockwave is speed into time. We already did this, and this is what we got. Okay, important point was when signal becomes red, okay, flow becomes 0 and density becomes jam. And this signal becomes green, opposite. Okay, initial flow is 0, final one is full. Initial density was jam, and the final will be how much? If in this question they did not give me this 75, can you see the relationship between jam density and this one? We already dragged it, we saw it earlier. What is the relationship between jam density and the density at saturation fluid? What is the relationship? Can you see? One is 150, the other one is 75. What's the relationship? If I have one, can I calculate the other one? What's the relationship between 150 and 75? Double. Okay? One is the double of the other. Okay? And this is the relationship if you have derived earlier. So it's not random. If you know one, you can know the other. There. Okay? Yeah. Okay. Now we have the Greenshield model. Okay. The Greenshield model says speed equals to this thing. Okay. Space mean speed equals to this thing. Where UF is the free flow speed, K is your density, and Kj is your jam density. Okay. This is the equation for Greenshield. We have used it earlier. Okay. Let us term this ratio K upon Kj as eta. Okay. So K upon Kj is eta. Okay. Now I have, if I go back to the shock wave, I have K1 and K2. So I can have eta 1 and eta 2. Okay. If I use K1 in the ratio, it becomes eta 1. If I use K2 in the ratio, it becomes eta 2. Clear? Okay. So we simplified this equation by removing this ratio with eta. And eta has a subscript either 1 or 2. Clear till now? Okay. Now the equation of the shock wave was Q1, Q2, K1, K2. Okay? This is the equation of the shock wave. Now, in this equation, and we also know that, so this is the equation of the shock wave, and we know that Q equals K into U. This is again the basic equation, the one which we have seen in traffic engineering, the one which we have seen in this course earlier, the one which we used here. We used it. Okay. This is the equation for K. Oh, sorry, this is the equation for U. Okay. If I multiply this U with K, it becomes what? Q. Clear? Okay. Now, I have Q1 minus Q2. So this will be replaced by Q1 will be replaced by US1 into K1, and Q2 will be replaced by US2 into K upon K1 minus K. There. Okay. Now US1 equals to what? According to Greenshield, US is equal to. Okay. So now I go back to this equation. I will replace US with this equation. Clear or not? Okay. So this is what they have done. Clear? Okay. What else? Okay, so now in this equation, I know that eta is basically the ratio of k upon kj, right? So if it is eta 2, that means k2 upon kj, and if it is eta 1, that means k1 upon kj, right? Okay, so remember k1 is also here, and then you have k1 upon kj here as well. Got it? Okay. So what we will do, we will open the two brackets, both the brackets. Okay, you can see UF is over here and UF is here as well. Okay, but when you open the bracket, UF will be multiplied by both these terms, right? So you have some terms which have UF in them. Okay, so all the terms, sorry, UF in them. Okay, so I have taken this term UF K1, UF K2. Okay, and this is how it is written now. Okay, so I have taken from some of the terms, I have taken UF as common. The term is without eta. Okay, so there were two terms without eta, UF into K2 and UF into K1. So I have taken UF outside, so I have K2 minus K1. Okay, and I have these two. Okay, where we have K2 and K1 and so on. Okay, so in this, now I will replace the value of eta with k upon kj. Okay, so this becomes k2 upon kj, this becomes k1 upon k. Okay, and there is already k1 and k2 here. So when you open it, you have, it will be squared. UF is common. Okay, and kj will be common, right? Eta is k upon kj, right? You will have upon kj here, upon kj here, and UF here. So the other bracket is UF upon kj with this. Got it? So k2 minus k1, k2 square minus k1, and k2 minus k1. Okay, so I have these, and this can be opened as this, right? The square can be opened as this, k2 minus k1 into k2 plus k1. Clear or not? Any problem? Okay. So you can see here k2 minus k1, k2 minus k1, k2 minus k1. Gone. Okay. So what do we have here? If you cancel all of them, what you will get? After cancelling out k2 minus k1 from everywhere, you will get UF minus UF again. Okay, k2 upon kj, k1 upon kj, right? Okay, and what was this ratio? E. Okay, so this becomes eta 2 and this becomes eta 1. That's right. Okay, now you have UF here, UF here. You take it outside. Clear? Okay, any problems? Okay, So this is the final equation you have got for calculating the speed of the shock wave according to Greenshield model. Remember this is coming from here. Okay. There no? Okay. When the density before shock wave and after shock wave is almost equal. If the density before shock wave and after shock wave is almost equal. So K1 equals to K2. K1 equals to K2. So I have eta 1 and eta 2 here, right? What was eta 1? K1 upon Kj. This one was K2 upon Kj. So if both of them are equal, K1 and K2 are equal, the eta will be equal as well, right? Because Kj is a constant. Okay? So they become equal. So instead of writing eta 1 plus eta 2, I just simply write 2 eta 1. Okay? So you have a shock wave, but the shock wave did not affect the density. Okay? Then the equation simplifies to this much. Because both etas are equal. Eta is depending upon density, right? They are not. Okay. Let's say we have a stopping shock wave, signal going to red. Okay. When signal becomes red, the density becomes what? Jam density. So remember, eta was density upon jam, right? So if density is jam upon jam, 1. Pardon? Okay. So again, it will be eta 1 plus 1. If it is 1, then I can open the bracket. Okay. 1 here, gone. So you only have UF into eta 1. There? Any questions? Okay. Then the other way around. When signal becomes green. Okay. So now which eta is 1? When signal was red, the final density was jam density, right? Now signal became green. So which density is jam density now? We have initial and final, right? Before, right? So eta 1 is 1. Eta 1 is 1. Okay. So again we'll do the same thing. Eta 1 will replace by 1. This will become 1 plus 1. Still 1 minus 1 cancel out. Okay. So whether signal goes from green to red or red to green, the value is same. So according to Greenshield model, the speed of forming wave is equal to speed of recovery wave. This is forming, right? Q is forming, and here Q is recovering, reducing. The speed is same. Got it? Okay. What else? Yeah, you can, because we have eta 2 here, okay? So you can go back to this equation and you can replace eta 2, or you can rearrange it for eta 2. So you open the bracket, US 1 equals to what? UF, I'm opening the bracket, okay? Minus UF into eta 1. I'm doing it for 1 or 2? 2. Okay, yeah, important point here, the speed will not be same because eta 1 and eta 2 are not equal. Sorry for that. So yes, the equation looks same, but eta 1 is not eta 2. Okay, so the value will not be same. The equation is same. Okay, so I want the equation for eta 2, right? Okay, so eta 2 equals to what now? What do I do? No, just eta 2. From here. No K. I'm taking eta 2 directly. So from this equation, eta 2 equals to what? So this will go here, right? So UF minus US2 upon UF, right? Okay. this is coming from this basic equation. Okay. So for example, you want to calculate eta, but you don't have densities. So this is another way of calculating eta if you have a speed. Okay. So now you will go back to this equation. You will take this value here and put it here. Eta 2 value. Okay. So it will become minus uf into this whole thing. Okay. And you can simplify it to this much. Okay. Clear? So summarizing. Okay. I will not move forward. Just to summarize this. And you guys came late as well, so cannot complain. This is the Greenshield model. Okay, in the Greenshield model, we are replacing this ratio with eta. Okay, then we go back to the equation of Shockwave. In the Shockwave equation, I have this thing. Okay, so Q can be replaced with this. All these Q's will be replaced with this. Okay. And US will be replaced with the Greenshield equation. Got it? Okay. And then we do simplification here, there, whatever we can cancel out and blah blah blah. And after that we got this equation. The speed of the shock wave according to Greenshield model. Okay. And then these are special cases. When eta 1 equals to eta 2, when you have forming shock wave, when you have recovery shock wave. Okay, and you can further simplify the equation. You can remove eta from the equation by going back and removing eta in terms of US and UF. Okay, you can do the same thing for eta 1 as well. Remember this eta 1 here. Okay, so the same thing can be put here for eta 1. The same thing which you did for eta 2. The only thing which will change is US 2 will become US 1. That's it. Clear? Okay. Any questions? Okay. Thank you.